can discuss about the equivalence of functional dependencies. That means check whether two given sets of functional dependencies of a relation are equivalent or not. So first of all, consider the definition. Suppose you are given with a relation R and with two different sets of functional dependencies of the same relation R. X is a set of dependencies of the relation R and Y is another set of dependencies of the same relation R. Okay, and you are asked to check whether this X and Y are equivalent or not. Then what we want to do? We want to check whether one set is the subset of other, or in some other way we can say, we can check whether one set forms the superset of other. That means if X is a superset of Y and or Y is a superset of X. If for the given sets X and Y, if these two conditions are valid, then we can say both X and Y are equivalent. What is the step we want to perform? We want to check whether X is a superset of Y or Y is a superset of X. If this one is valid and this one is also valid, then we can say both X and Y are equivalent. So this is about the logic of equivalency between functional dependency set. Okay, so consider X and Y, two different functional dependency sets of the given relation R. So the first step, if all the functional dependencies of X can be determined from functional dependencies that are present in Y, then we can conclude that Y is a superset of X. How to check whether this Y is a superset of X? This one, Y is a superset of X, or else we can say X is a subset of Y. These two are the same. If Y forms a superset of X, that means X is the subset of Y. We can say it is Y covers X. This notation for this is, if Y covers X, we can represent either like this or this. Y covers X means Y is the superset and X is the subset. This Y covers X can be represented either like this, Y superset X or X subset Y. Okay, how to check this? How to check whether Y covers X? For that, you want to check if all the functional dependencies of our subset X can be determined from functional dependencies that are present in our superset Y. Once more, we need to check the functional dependencies present in our subset X can be determined from the dependencies present in superset Y. If it is valid, then conclude Y covers X. Similarly, we want to check one more, that is whether X covers Y. X covers Y means X is the superset and Y is the subset. X covers Y. X is the superset, Y is the subset. The notations are either like this one or this. X covers Y can be represented X superset Y or Y subset X. In order to check whether this X covers Y, what we want to perform? We want to check all the functional dependencies of our subset. Which one is the subset? Y is the subset. All the functional dependencies of Y can be determined from the functional dependencies that are present in superset. Which is the superset here? X is the superset here. So, all the functional dependencies of our subset Y can be determined from the functional dependencies that present in the superset X. If it is valid, then we can conclude that X is the superset of Y or Y is the subset of X. These are the equivalent notation. If it valid, we can say this notation can be called as X covers Y. Okay, then after checking this one and this case also, that means after checking whether Y covers X and X covers Y, then we can consider this one. That is, if both 1 and 2 are satisfied with the given set of functional dependencies X and Y, then we can say X equal to Y, or X and Y are equivalent functional dependency sets. Okay, so this is the steps that we want to follow in order to check whether the given set of functional dependencies are equivalent or not. Okay, we want to check whether Y covers X and this X covers Y. If these two are valid for the given set of dependencies, then we can say these sets are equivalent. Okay, so consider example, then understand what are the steps we want to perform in order to check whether X covers Y and Y covers X. So the question is like this. A relation R with set of attributes like relation R with attributes A, C, D, E, H, and two sets of functional dependencies are like X is a set with three different dependencies like A implies C, AC implies D, E implies ADH. And the next set Y is A implies CD, E implies AH. And the question is, which of the following holds true here? The first option, X superset Y. What is the meaning? X superset Y means whether X covers Y. Y superset X means Y covers X. If these two conditions become valid, then we can conclude X equal to Y. Okay, now we can check this one after another. So these are the set of dependency given for the relation R. Okay, so first we can check whether Y covers X. The notation is Y superset X. The superset part contain Y and subset part contain X. Understand this notation properly. Then this steps become very easy. Actually, this question is somewhat tricky. So understand this concept and the notation properly. Then this step become very easy for you. Okay. The superset part contain Y and the subset part contain X. From this notation, it is clear that we want to check whether this Y or the superset covers our subset dependencies. So what we want to do then, for checking this, we want to consider the closure of subset attribute. We want to consider the closure of subset attributes. That means move to the subset now. Which one is the subset? X is the subset here. So move to here. Exit. Then find the closure of LHS part of our functional dependencies listed here in this set X. So what are the closure? A closure, AC closure and E closure. Find out the closure of subset dependencies. LHS part of our subset. So here A closure, AC closure and E closure. We want to find this closure now. The LHS part of our subset. Okay. Then the twist is we want to find the closure with respect to the dependencies listed here in the superset. Okay. We want to find the closure of our subsets LHS part with respect to the set of dependencies present in the superset. So keep this point in your mind. Then this task become very easy for you. That is, in order to check whether Y covers X or X covers Y, first understand which one is the subset and which one is the superset. Then note this point. That is, we need to find the closure of subset with respect to superset dependencies. Keep this in your mind. Find the closure of LHS part of subset with respect to superset dependencies. In short, we can say find out the closure of subset with respect to superset. Subset closure with respect to superset. How to do this? So here in this notation, X is the subset, right? This superset part contain Y. So we want to find the closure of LHS of our subset. So LHS of our X contain A, AC and E. So we want to find the closures. A closure, AC closure, E closure with respect to dependencies listed in our superset. So keep this one point in your mind, then this equivalency check become very simple for you. Okay, this is actually an important, very important topic regarding objective type exams, gate exams, net exams, etc. So keep this single point in your mind, then the step become very simple. Okay, the trick is, or the tip is, find the closure of LHS part of your subset with respect to the dependencies listed in your superset. Okay, so X is this one. So closure of LHS part of X, A closure, AC closure, E closure with respect to the dependencies listed here in the superset. So A closure form thus A directly included in this closure set. Then with respect to this dependency of our Y, we can also include C and D here. Nothing else is present here. Okay, so the closure of A is A, C, D. Now to find this AC closure. How to find? So again include this AC directly. Then here we have the same expression. This A derives CD. So using this dependency, this D also included here. Okay, so the AC closure include A, C and D. Now want to find this closure E closure with respect to superset Y. So E closure include E directly included, then from E we can derive A and H. So AH also included here. So from this A we can derive C and D also. So these are included here. Okay, now check, based on the definition, we want to check whether the dependencies of our subset are derived from the superset dependency. For that, the first step is derive the closure of subset with respect to superset. That is done here. Now check whether the subset dependencies are held here or not. How to check? So the first dependency in the subset is A implies C. A implies C. So move to this closure of A. Okay, so the presence of this C in the closure set, we can say the dependency A implies C of our X is derived from the given set of dependencies of our superset Y. The presence of C here in this closure of A, it is clear that the dependency A implies C of our subset X is derived from the given set of dependencies in our superset Y. So this is valid. Next, dependency in X is AC implies D. So move to the closure of this AC closure. Okay, so the presence of this D here in the closure set of this AC, the presence of this D indicates the AC implies D. Dependency of our X is derived from the given dependencies of our superset Y. So this is also derived using this Y. Now check. Now the third dependency in set X is E implies ADH. Okay, so move to the closure of E. The presence of this ADH, A, D and H in the closure set of E, it says that the dependency E implies ADH of X is derived with the help of dependencies present in our superset Y. So these are the three dependencies present here in X, and all these three are derived using this corresponding closure set. So finally we can conclude that this one is valid. That means Y forms the cover of X, or Y is the superset of X, or X is the subset of Y. That means Y covers X dependencies properly, or the dependencies in X can be derived properly with the dependencies present in our superset Y. So this one is a valid case. Y derives X. Okay, so the first condition is valid. Now we want to check the next part. That is, we want to check this X covers Y or not. So in this notation, X is the superset and Y is the subset. So what is our principle? The closure of subset with respect to superset. The first step is find out the closure of subset with respect to superset dependencies. Keep this point always in your mind. Then this equivalency checking task become very easy. Okay, closure of subset with respect to dependencies of our superset. In this notation, which one is the subset? Y is the subset. Which one is the superset? X is the superset. So the first step is find the closure of subset with respect to superset. Okay, so in Y, in subset Y, we have two attributes in the LHS part of this given dependency. One is A and another is E. So find this A closure and E closure first. With respect to what? With respect to the superset X. Okay, so the A closure is, from this we can, A closure means we can directly add A to our dependency. From this given dependencies of X, we can derive C, then using this AC, we can derive D also. Nothing else. Nothing more exists. So this is the closure of A. Next is closure of E. Okay. So the E closure is directly add E to the set. Then E can derive ADH. ADH. Then A can derive C also. That C is also included here. So the first step is over. Derives the closure set of subset, LHS part of the subset, with respect to superset dependencies. Okay, now move to the subset dependency. And first dependency here it is A implies CD. The LHS part contain A. So move to the closure of A. Okay, whether this A implies CD can be derived with respect to the dependencies of our superset X. How to check? In order to validate that if this A implies CD can be derived with respect to this X dependencies, check whether this C and D exist here in this closure of A. Exactly, the C and D are present here in the closure of A. That means the A implies CD. This particular dependency of our subset Y can be derived or derived with respect to the dependencies listed here in X. And the second dependency here it is E implies AH. So here the LHS part contains E. So move to the closure of E. The presence of this A and H here in the closure set, the presence of this A and H indicate E implies AH of our subset Y is derived properly with respect to the set of dependencies listed here in the superset X. So all the dependencies are checked and evaluated, and the condition is true for all the dependencies of our subset. Now we can conclude that this particular statement, that is X covers Y, X superset Y, or y subset x or x covers y is again valid. Okay, x covers y is valid here. Okay, so this was the given question from our previous steps. It is clear that first validate this y covers x, that became true in our example, and again this condition also validated as true, that is x covers y. This one become true, this one become true. If both are valid, then we can conclude that x is equal to y or x is equivalent of y. So this is the right answer for the question. X is equal to y. Okay, or x is equivalent to y here. Now we can consider another change. That means if you are given with the option like this, A is given as, for the same previous example, the options are like this: x covers y, B is y covers x, and C is x equal to y. What is the meaning of this? X covers y means x is the superset and y is the subset. How can we notate this? X superset y or y subset x. Y covers x means y superset and x is the subset. How can we write? Y superset x or x is a subset of y. Okay, so understand the meaning of this. Consider another example with two different dependency sets, S1 and S2. With these dependencies are listed here in S1 and S2. And the options are like this: A, S1 subset of S2, B, S2 subset of S1, C, S1 equal to S2. What is the meaning? Here the notation is S1 subset of S2. From this it is clear that we want to check whether S2 covers S1. Here the superset part is S2, subset part is S1. That means S2 covers S1. Here S2 is the subset and S1 is the superset. That means we want to check whether S1 covers S2. Okay. So the representation is like this, and we are going to check whether S1 subset of S2 or whether S2 covers S1, because the superset part contain S2, subset part contain S1. So what is our step? First, we want to find the attribute closure of our subset with respect to superset dependencies. From this notation, it is clear that which one is the subset? S1 and superset is S2. So the step 1 is find the closure of subset attributes, LHS part of S1 with respect to the dependencies listed in our superset S2. Okay, so what are the LHS part of S1? A, B and AB. So find the closure, A closure, B closure and AB closure with respect to superset dependencies. So now the A closure become A directly added here, then B. Using B we can derive C. A again can derive C and D. So D is already present here, so D is also added. So this forms the closure of A. Now B closure with respect to S2. B directly added here, then B can derive C also, nothing more. So C is also added, so B closure form B and C. So next is AB closure. AB directly included in the closure set. Then move to here. This A can derive further C and D. And B can derive the C, but C is already included here. So this is the closure of AB with respect to S2. Now move to the subset. And first dependency here it is A implies B. The LHS part is A. So move to A closure. The presence of this B here in the closure set indicates that this A implies B of S1 is derived with respect to set of dependencies listed here in S2. Again, next is the dependency. Here it is B implies C. So here LHS part is B. So move to B closure. Okay, B closure, the presence of this C here in the closure set indicates that the dependency B implies C of S1 derived from given dependencies of S2. This is also comes true here. Next dependency in the subset is AB implies D. The LHS part is AB. So move to the closure of AB. So the presence of D here in the closure set, it is clear that the dependency AB implies D of our S1 derived from the given dependencies of S2. So all the dependencies are evaluated or checked here, validated, and conclude that all the dependencies of S1 are derived properly with the help of dependencies listed here in the superset S2. So now we can conclude that S1 subset of S2 is a valid statement, or S2 covers S1. So this is a correct statement. So we can check the other case now. We want to check the other case, that is whether this S1 covers S2. S2 subset of S1 means S2 is the subset, S1 is the superset, or S1 covers S2. We want to check whether S1 covers S2. In the previous slide, we have discussed or we have concluded that S2 covers S1. S2 covers S1. Now going to check whether S1 covers S2. So which one is the subset? S2. Which one is the superset? S1. So our step is find the closure of subset with respect to superset dependencies. So which one is the subset? S2. Move to here. Find the closure of LHS part of subset. LHS part contains A, B, and this A is repeating. So find the closure of A once and closure of B. With respect to what? With respect to the superset dependencies. Superset part contains this S1. So A closure is directly add to this closure set. From here A derives B. This B can derive C. So C also included here. Then this AB can derive D. This is the closure of A here. Now the B closure, B directly added to this set, closure set. Then this B can derive C. So C also included here. Nothing else is possible. Nothing more is possible. Okay. So we can stop here. The B closure contain B and C only. Okay. After deriving this closure part of subsets, now we can go to the subset. Which one is the subset? S2. So the first dependency here it is A implies B. LHS part is A. So move to the closure of A. Here the presence of this B here indicates that this A implies B of S2 is derived with the help of our set of dependencies of S1. Again, here we have one more dependency starting from A, that is A implies CD. Okay, so the presence of this C and D here in this closure set, it is clear that A implies CD of our S2 is derived properly with the help of dependencies listed here in S1. Again, we have one more dependency left here, that is B implies C. So here the LHS part is B. So move to B closure. Okay. So from this, the presence of this C here in the closure set, it is clear that B implies C of S2 is derived properly with the help of dependencies listed here in S1. Right. So we can conclude that S2 subset of S1 is a valid statement, or S1 covers S2 properly. Okay. So we have concluded both S1 covers S2 and S2 covers S1. This became valid and this also became valid for our given example. From this, if both are valid, then we can conclude that S1 equal to S2 or S1 is equivalent to S2. So the option C is again true for our second example. Okay. So okay, consider the third example. Two set of dependencies S1 and S2. And the option like this. And we want to check which one holds true here. Okay. So first go for S1 subset of S2. S1 is the subset and S2 is the superset. Right? So first step is find the closure of subset. LHS part of subset with respect to superset dependencies. Here S1 is the subset. So the closure of S1 is A closure and B closure. And this closure with respect to superset. The A closure is A, B, C, D. A, B, C and D. B closure is B directly added here. From B we can derive C also. Now check whether the subset dependency A implies B is derived with the help of this S2 dependencies or not. A implies B, the LHS part is A. So move to A closure. Here one more dependency, A implies C. Okay, so move to this A closure, and the presence of this B and the presence of this C indicates that both A implies B and A implies C of S1 is properly derived with the help of dependencies of S2. Okay, and one more dependency is left here, that is B implies C. The LHS part is B, move to B closure. The presence of this C indicate B implies C of S1 derived from given dependencies of S2. So this is also possible. So we can say S2 forms the cover of S1 or S1 is the subset of S2. Okay. So this one is a valid statement. Now we can check the other case, that is whether S2 subset of S1 or the S1 covers S2 or not. Here the subset is S2, superset is S1. So find the closure of LHS part of subset with respect to superset. Here the subset is S2. So closures are A and B. A repeating twice. So find the closure of A once and B closure also. A closure with respect to superset S1. A closure is A is directly added, then from this dependency it can derive B and B can derive C. And similarly the B closure is B is directly added, then using this dependency C also added. Nothing more is possible. Okay, now go to the dependencies of our subset S2. First one is A implies B. The LHS part is A, so move to A closure. Here the presence of this B indicates A implies B of our S2 can be derived properly with the dependencies of S1. But here we have one more dependency starting with A. A implies D. So the absence of D here in this A closure, it is clear that we can't derive this dependency using the dependencies listed here in this S1. The absence of D here in the closure of A, we can conclude that the dependency A implies D of our subset S2 can't be derived with the help of this dependencies listed here in the superset S1. So we can stop right now and conclude that A implies B of S2 derived with the help of dependencies of S1, but A implies G of S2 can't. So we don't want to continue further. We can stop right now and conclude that this one is a wrong statement or this one is not valid for the given sets. So here S2 subset of S1 is not true or it is not holding here. That means S1 is not a cover for S2. So after validating whether S1 covers S2 and S2 covers S1, we can conclude that this one was a valid statement. S2 forms a proper cover for S1. But this was not true for the example. Right? So, which one is true here? Option A is the right answer. If both are valid, then we can conclude this one, that is S1 equal to S2. But in our given example, this one is not whole true. So the right answer is S1 subset of S2, or S2 forms the cover for S1. Okay. So these are all about checking equivalency between two different sets of functional dependencies of a given relation. Okay, and in our coming video we can discuss some more gate questions regarding this equivalency, attribute closure and functional dependencies. Okay.